even reasoning about the left-hand side of the implication. And kind of part of what I find really interesting in this about all of this is we're discovering this as logicians, but of course, I think most logicians and computer science people are so much smarter than me that maybe they don't have these issues. But there's all this cognitive science literature about people saying if X, then Y, and they never think about, the not X case, basically, like when the antecedent of an implication is false, and that all these logical fallacies that come out of it. And I think there's a lot when you add time that sort of even like compounds this.
I think that's just the intro of your talk, is it?
In a sense, yeah. Uh, uh, I, hopefully I have something a little more interesting to say, but yeah, I think
I
if you
guess
take
that's
one
how
thing
I'll
away,
introduce you.
yeah. If I get this right, then yeah, eventually, everybody will understand. Yeah.
So I think we have a few people here. I am going to start. I'll introduce you in about 2 minutes, and then we'll start at 7:05. I don't know
Whatever.
which you are on Eastern time. So
I'm on Eastern time, so I'm totally fine. It's like it's a reasonable hour of the morning for me. Like I'm not, yeah. It's like 9:30 a.m., so all good.
let's get started. So, hello everyone. Welcome to the verification seminar series. Today with us we have Siddhartha Prasad. He is a PhD student at Brown University. And he has a nice introduction. We floated it, but the last line is something that I think everyone here can relate to. So he says, I have written code that doesn't do what I want it to do, and I want to spare everyone else the indignity. Such a beautiful line. I'm going to copy that, Siddharth, whenever I try to give such talks. Uh, we were just talking about how difficult it is to come up with a specification and the joke that he's put up on the first slide. These things become more and more difficult as you add time as a modality. And today, Siddhartha is going to talk to us about misconceptions in LTL and eventually understanding. Over to you.
Thanks. Yeah, so you all know propositional logic, right? It lets us talk about what's true or false, and but it doesn't really let us naturally say things like eventually the traffic light will turn green, or, once I get the lock, eventually I have to release it, or my mother's favorite, don't get a cookie until your homework's done. But a standard way to express properties like this is linear temporal logic. And with just a small set of temporal operators added to propositional logic, LTL is surprisingly expressive. And this expressive power is kind of why LTL has been a core logic in verification and synthesis for decades. But it's no longer confined to just those settings. More recently, it's been showing up in domains like robotics, business process management, and AI planning nowadays. And given that range of use, it's not surprising that it shows up in a bunch of different syntaxes and sort of different presentation modalities. But the bigger shift isn't just syntactic. In many of these settings, the starting point isn't a logical specification, but an informal goal. And translating those intuitions into precise temporal formulae, even with this compact vocabulary, is really hard. Here's one way that subtlety shows up. So I want all of you are very smart, but I want you to put yourselves in the shoes of a student. There's some LTL formula X until Y. Which of these two is really the semantics of X until Y? Option one is X is true until time T, and at T, Y becomes true. And option two is the same, except at time T, Y becomes true and X becomes false. So quiz time. Give me a one or two in the Zoom chat, like option one or option two. Like which of these are really the semantics of LTL? Anybody? Okay, great. I'm actually seeing like a mix of one and two, and I think that's kind of the point, right? So let me, in fact, like the correct answer is one, but that doesn't mean that people who chose two are being irrational here. Here are two properties that are of the form X until Y that match each of the semantics. In the first one, after the battery is full, the robot is allowed to leave the dock, and but that doesn't mean that it has to immediately leave the dock. In the second, the motor is understood to have turned off once it reaches the destination. Both are really natural interpretations of until, depending on the context you're in. Properties aren't written in the form of a sort of written from a neutral semantic vantage point. They're written with goals, expectations, and domain understanding in mind. Sort of as Perlis famously put it, you can't move from the informal to the formal using formal means alone. So when someone chooses option two, I don't want to dismiss that as an error. It's a plausible interpretation carried over from informal reasoning. But LTL is a formal language with precise semantics, and by that semantics, option two is incorrect. And that's what in this talk I will call a misconception. It's a plausible, coherent interpretation that fails to match the formal semantics. And it turns out that these kinds of misconceptions are surprisingly pervasive. Over the last few years, our lab at Brown has been engaged in a project designed to understand the typical misconceptions that learners and even experts have when it comes to LTL. In order to do so, we've carried out several rounds of studies across different syntaxes, visual representations, kinds of tasks, and levels of expertise. And one useful outcome from our studies is a set of instruments, think of them as quizzes, that instructors can deploy in their classes to understand how well their students understand the logic and what weaknesses they have. We've deployed this survey over multiple years in audiences, analyzed several thousand responses, and built a catalog of typical misconceptions that LTL learners and even experts have. I put part of this up on screen to give a sense of its breadth and size, but it's not important to spend time looking at it in detail. I think the main thing is that one thing I'll point out is that exclusivity of the until misconception we talked about does show up here. The key thing is that with this sort of insight, I hope will lead to better tools, more intuitive logics, and better instruction. For example, sort of these findings have already inspired changes to modeling tools like Alloy 6 and Electrum and how they present temporal structure. But in the first part of the talk, I really want to focus on the instructional side. While we have meaningful quizzes and a rich catalog of misconceptions, how exactly can instructors operationalize these insights? I have to teach classes myself, and I recognize how hard it can be to incorporate new materials in a class, right? You have to adjust the curriculum to accommodate for materials, come up with new assignments, and if you have TAs, you even have to train them to build fluency with these changes. Furthermore, okay, your students make certain mistakes. Now what? They need explanations for what went wrong, need additional drill problems, and they need checks to like let them know whether they got these additional questions right. And all of this assumes a class setting. Independent learners, and there are many of them for LTL nowadays, have even less support. So with this in mind, I've sort of distilled our group's research into an adaptive LTL tutor, and the tutor operates on a two-loop model. It starts by generating a multiple choice question set grounded in the misconception catalog. And as students answer questions, it gives them feedback about their specific mistakes, but also builds a model of their underlying misconceptions and gives more general feedback at the conceptual level. Finally, it tailors subsequent question sets to exercise the misconceptions previously exhibited by the learner. So I want to get into kind of the technical core of this work, which is the question generator. I want to kind of dig into this a little bit more. Say we have a question asking a student to translate this sentence to LTL. The robot's motor is always on until it reaches the destination. Here's the correct answer. So here's a question. How do you use this information to generate a multiple choice question? One approach is sort of classical mutation. Sort of program mutation is a software engineering technique that uses random syntactic variation to create mutants of a correct program. Say here, randomly replace the binary operator, change associativity, or swap operand order. And these could plausibly be used as distractors in a multiple choice question, right? But they don't really test the real difficulties that students have. For example, if you look at the second option here, it's highly, highly unlikely that a student would pick this. If we choose bad distractors, we can't really exercise or evaluate the real difficulties students have. So what can we do instead? This is where the catalog of misconceptions comes into play. Instead of applying random mutations, we can mutate correct answers to embody specific misconceptions. We call this semantic mutation. Let's look at the implicit G misconception from the catalog, which is a very simple one that people tend to have. It has to do with students assuming that the globally operator in LTL implicitly applies to all of a formula. When applied to the question we've been looking at, you can sort of embody this misconception by simply dropping the outermost G. That is, produce a formula of the form X holds now rather than X always holds. Similarly, you can embody the sort of the exclusive until misconception we've been talking about, where the learner believes that the until operator forces the negation of its left subterm to hold. Basically, by pretending that until has those stronger exclusive semantics, aka semantics option two we talked about earlier. The key insight is that each misconception can be expressed as a set of rules that can be used to guide mutation. Here's a few of them. There's several more. Basically, by analyzing the structure of a correct answer, we can mutate it to embody misconceptions from the catalog. Now, these rules don't aim to cover every possible manifestation of a student's misconception, but they do provide concrete representative instances of it. And we've tested this claim that misconceptions can be used to generate better distractors. We ran the tutor with misconception-based sort of semantic mutants and include one random syntactic mutant as a control. And then we measured how often each option was selected. So on the x-axis is sort of the selection odds, the odds that an option is chosen normalized by chance. And as you see, for all the different kinds of misconceptions versus syntactic, students tend to choose that sort of syntactic mutants least often. I think this shows us two things. One, our students are actually using the tutor in good faith and not randomly guessing, which is always a concern in education. But more importantly, better distractors in multiple choice questions come from modeling the kinds of sort of incorrect semantics people may have. Okay, this is great, but we have a way to generate questions. But the next question is, how does this actually help students learn, right? The first thing the LTL tutor does is it gives feedback at the question level. Say the student chooses option five, but the correct answer is option two. They're shown why their answer is incorrect in the form of a counterexample trace. This is pretty standard in formal methods. And a visual metaphor detailing the relationship between their answer and the correct solution. And if the student wants further insight, they can walk through the evaluation of the correct answer over the counterexample trace using an interactive stepper. Basically, like the tree above shows the formula ASD and how each formula or subformula is satisfied or not at a given moment. More importantly, and this is the key insight, if a student selects the wrong answer, we have a sense of why they did so. In this case, they picked the mutant generated from the exclusive U mutation rule. This is an indicator that they may have the exclusive view misconception. If they show a pattern of selecting the options associated with the same misconception, the tutor gives them feedback at the conceptual level as well. Feedback for the exclusive view misconception looks something like this. Notice that it doesn't relate to a specific problem, but rather gives the student relevant insight into the behavior of the until operator. We start by stating a plausible belief, then we contrast it with the correct semantics, and then we walk through a concrete example. This follows a well-known educational pattern called a refutation text. Basically, it's been shown that this sort of format is really well suited to combating misconceptions. So zooming out, there's this two-loop mode, which means that learners get tailored feedback both at the question level and at the conceptual level as they uncover, attend to, and address their misconceptions. So does the tutor actually help learn LTL? This is a tough question to answer since it's adaptive to misconceptions. As learners demonstrate issues and ability, it makes the questions harder in a way that's tailored for them. So you can't just look at, their accuracy. Instead, we model how likely it is that a question is answered correctly, given some factors unique to the student, unique to sort of some features of the seed formula, sort of size, verification hardness, number of literals, and the number of questions they previously answered in the tutor. Controlling for inter-student variation and the difficulty of a seed formula, we try and quantify the tutor's ability by seeing that the likelihood that a student gets a question correct goes up with the number of questions answered. And as you might expect, students do improve with practice. After controlling for question difficulty and individual differences between students, each additional question a student answer gives us a 0.7% increase in the odds of answering correctly. This sounds small, but it's actually super statistically significant, and it accumulates. Over 50 questions, that means that the odds of a correct answer increase by 43%. To summarize, we've distilled our expertise in LTL and LTL misconceptions into a tutor. All you need is a brief introduction to LTL or even just propositional logic to get started. This prerequisite aside, it's not built just for novices or just for experts. This means that you, as an instructor, can use this in various courses, deliver your usual lecture on the topic using your preferred framing, and then have your students use the tool to grow and reinforce their learning. You can try it online at ltl-tutor.xyz. We use it for some of our courses at Brown, and I've been really encouraged by how it's helped students interact with LTL. I also think what's really nice about it is that it gives students an unending adaptive set of practice problems without me as an instructor having to put in any additional effort. It gives them feedback, and if they want more questions, it keeps tailoring more and more questions and practice for them sort of on demand. Okay, so far I've been talking about the instructional side of LTL. I'm going to ask a slightly uncomfortable question now. Why learn this at all? If someone needs an LTL formula today, the obvious thing to do is just ask an LLM. You paste the requirements in, it gives you something that looks like a reasonable formula, and you're good to go. Or not, right? I suspect everybody in the Zoom call already sees the issue with that, but people are still going to do it. Like, no matter how much we, as sort of people with an understanding of how LLMs work, etc., sort of caution people, they're still going to do this. The question is then, how can we help somebody have the confidence that the formula they ended up with is actually the right one? So I gave this description to Gemini, and what I got is this as a result. Right? Sorry, I gave this description, I guess. So is this correct? I don't know. I mean, in fact, I gave the same query to ChatGPT and I got a completely different answer. And really, running the same query through the same LLMs can also give you different answers. Okay, so we have two candidates here. Which one is correct? I don't really know, right? My position here is that we do a lot of human in the loop stuff already. Humans need to be in the loop, and we do this all the time when the stakes are high, right? Your computer pops these up all the time. The key insight is that any human activity in the loop needs to be meaningful and moderate. I call this the responsible human model. So to go back, I'm going to do quiz time again. Here's the same formula. The red light is on exactly once, or exactly in one state, not necessarily the first. And there are two traces, option one and option two. So again, in the Zoom chat, give me a one or two, depending on which of these traces satisfy the property. Okay, amazing. I think all of you said two, right? What's interesting is that the first trace is accepted by one of the formulae given to me by LLMs, basically Gemini, and the second is only accepted by the other one. What we've basically done is we've used the concrete traces to be able to distinguish between the abstract formulae. This is actually a well-known principle in cognitive science. Humans are way better at reasoning about concrete artifacts than abstract concepts. And this is basically the idea I want to leverage in the second part of this talk for the system I've been calling PIC, which is pairwise iterative choice knockout. The idea is pretty simple. The user provides an informal spec to GenAI, which produces a candidate LTL formula. But before giving it back to the user, we run it through the semantic mutator to get a set of candidates that could each plausibly reflect the user's intent. We generate pairwise traces that distinguish between these candidates, asking a human to upvote and or downvote them until only one or no candidate remains. By running through the system, a user is able to sort through all kinds of possible semantic interpretations of their informal spec without even having to look at an LTL formula. While it doesn't correct for any inherent failings of GenAI, it uses sort of semantic insight to build confidence in any output one might finally get. Pick has a sophisticated way of partitioning the candidate space to optimize for information per classification. I'll put it up here for a second, but I think the idea is best explained in a two-candidate setting. So I'm going to start with pick informally. Given two formulae A and B, you compute the set difference between the language accepted by A and the language accepted by B, and ask humans to upvote or downvote concrete instances from these distinguishing sets. All of this works because of some computational properties of LTL. Closure, decidable membership, and tractable witness generation via Buki automata. I just want to take as an aside, as an educator, I rarely get to motivate my students why like all these like theory of computation sort of ideas matter at all. So it's nice to see them kind of in the wild in practice. But aside from sort of these computational theory ideas, this whole idea also hinges on this bit. Humans, how well can the humans classify? That is, like, how does any of this actually help? There's a corpus of cognitive science literature that says yes, like reasoning about concrete versus abstract artifacts, etc. But as computer scientists, we actually have data that we can compare it against. Remember the instruments or quizzes I mentioned earlier we used to identify LTL misconceptions in the first place? Well, we took three of those questions and used all the answers we received from experts as candidates. That is, these are the original semantic mutants that experts kind of wrote out when we gave them this, each of these questions and said, give me the LTL for this. Some of them were correct and some of them were wrong. I think the key idea is that we presented these questions to participants with no knowledge of LTL in the pick modality. That is, we only showed them the English language description and the traces to classify, and basically asked them to accept or reject those traces. Depending on their classifications, the tool eliminated candidates until they converged on a single candidate or no candidate at all. And kind of got a sense of what their answer was as a result. We could then compare the performance of these participants to those of experts in our original studies. And we found that they outperformed experts in two of the three questions and did about as well in the third. While this is super preliminary, this is really interesting, right? Like even experts get LTL wrong a bunch, but just by having people reason about the concrete artifacts of LTL rather than the abstract formulae and their semantics, we we can do much better. I think another interesting thing we found is that the number of classifications users had to take didn't scale with the number of underlying candidates. Since the space of semantic mutants can be quite large, like we can just run a semantic mutator a bunch, this is really good news. We can have every applicable misconception under the hood, and it doesn't make things onerous in terms of the classification task. So this is kind of, I was hoping that the rest of this talk, maybe I could answer questions and kind of deal with, talk about semantic mutation in other places or even these places where it might be useful a lot more, or even the LTL tutor. But kind of in a sense, what I really want, if I could communicate one thing, what I really want to communicate is that misconceptions aren't just mistakes, they're incorrect semantics in someone's head. And so you can use sort of principled cognitive science techniques to actually build catalogs of these alternate semantics. Once you have alternate semantics, you can really start building these sort of semantic mutators. It's not just LTL. There are a bunch of places where this shows up. And you can do a lot with a semantic mutator. Here are two examples. One is sort of education, so the LTL tutor, which, I'd love if anybody used outside of, I mean, in this call, people use it around here. And then the other is like sort of other workflows that help build confidence in LLM output, like as we get into this weird new Gen AI world, or even just help people explore the space of what their semantics around these things might be. So that's kind of the main part of my talk, and the rest I'd like to kind of, yeah, chat, if that makes sense.
Thank you. Maybe we can turn it into a discussion, but before that, it was an amazing presentation. Absolutely loved it. Thank you so much.
Thanks.
If there are any questions, comments, please raise your hand or unmute yourself. You can also post in the chat.
If not, let me ask y'all a question. How many of you teach LTL to your students? I'm kind of curious if you could raise your hands. I'm trying to understand. It seems to be super popular, but I'm trying to understand like LTL or similar logics. And if you do you kind of see these issues with them? Like, is this the kind of thing you might imagine? One, you might find useful, but two, um, do you see your students struggle with it? We certainly do. And I think this is an issue.
I taught a games on graphs course here at Ashoka, and students struggle a lot with LTL, especially the example you started with on the semantics of until.
Yeah, in fact, I think until release, right? Release, which is kind of a dual of until a little bit, is hard. And then weakness and strength of these operators. Yeah. Are there other logics that you teach that you think would, you know, teach or use that do you think like this idea of semantic mutation might be useful towards, right?
I think even
Like,
in propositional logic, it's useful in the first course as a discrete math course.
mhm. I mean,
That way on.
yeah, no, I think it makes a lot of sense. To give an example of, if I were to go back here, um, I want to point out that anything that has these three computational properties kind of benefits from this approach. So an example is I have a version of pick that works with regular expressions.
Hmm.
So I actually use it. It's a VS Code extension. I can post a link if anybody wants to use it, but here's what it does. I often have to write regular expressions. Uh, I'm pretty bad at it. I do give it to an LLM. I don't know if the LLM is correct. Regular expressions have these have tractable witness generation, decidable membership, and closure properties. So I can just LLMs are pretty good about remove at positing regular expressions. They're trained over them, and I'm actually able to upvote and downvote little words that we generate to be able to synthesize sort of the ideal regular expression that I want. And I use this all the time. So an idea I want to kind of put forward is if you can build a semantic mutator for it and the language has these three properties, you can kind of carry this over anywhere. And I found this really useful even for like small fragments. So regular expressions, small fragments of first order logic, things like alloy programs. As long as I can do some bounded model checking over them, I'm able to informally with this idea kind of plug and play. And 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 sometimes I get the semantic misconceptions for free. Yeah.
There's a question in the chat.
Uh, Before we move on, if I can make a small comment here.
Yeah, please, please go
Hi,
ahead.
this is Divyesh. So I come from the industry side, so I do not teach, but LTL formulae are used in electronic design automation, specifically to specify liveness kind of properties. And while there are application engineers who are quite adept at using some of the tools that are used in verification, not too sure if they are fully conversant in specifying the properties about the hardware, and I believe they often get the LTL wrong. So I was here just to look for, can some kind of help be provided to these
Hmm.
folks with LLM coming into picture? Not sure how many customers and stuff have started using this kind of a thing, but yeah, this tutor kind of a thing may be really helpful in certain settings. So it may have quite an application in the real world also.
Yeah, I think one of the things we've done is it's not tied to a specific curriculum and it adapts to you. I think I also saw this in the chat that like all the questions and answers are auto-generated from the catalog of misconceptions. We like do a bunch of automata manipulation in the back. So you can just keep going and it'll keep adapting to what you need by tracking your misconceptions. So I find that this is like really useful for I guess independent learners is a word we could use, but basically somebody, say, for example, in industry who doesn't want to take a full course in LTL, has a grasp of propositional logic and now wants to just make sure that their ideas and intuitions are correct. Often what I do is at one class a semester, I just give the link to students and I say, okay, just go. And I find there's this big improvement. I say nothing to them. They know propositional logic. They just kind of pick it up by this feedback loop. Sorry, I also I saw this question about what sorry, so I guess I can read them out but in chat. So a question about sort of a library of the most common LTL patterns in specifications with samples of how to use these. I believe one of these does exist. It's by Tim or Thomas Dwyer. I forget his first name. Uh, and these have got a lot of play. Um, uh, I think the problem is that the kinds of properties we're seeing in specifications really depend on the domain. So I think that like while things like release and like infinite, like things that map to verification hardness, Grover, are things that people use a bunch in verification and synthesis. Robotics people have a fully different vocabulary of what they want from LTL, and not to mention like I don't know, business process management people, where the actual patterns are a lot simpler sometimes, or seem simpler from like if I were to plot it on the like Mana-Bernoulli hierarchy of like how hard they are to verify, but often they're much longer and more complex in terms of just number of tokens and number of propositions in them and things like that. But the Dwyer patterns do exist, and we do use them sometimes to seed questions in the tutor as well. So the tutor does kind of try to work through some of the ones that at least verification people use. Um, Sorry, should I just go through the chat questions, I guess? Oh, if anybody has a vocal question, I can also answer. Yeah.
There is one question in the chat, and then there is one comment from Sujit. You can maybe
Mm-hmm.
take the question there, which is, are the and answers auto-generated from the catalog of common mistakes, or were they created by hand? I think you
That
also
they're
have.
auto-generated. Yeah. So we do some Buki. Actually, it kind of ties into this idea of when you start blank slate before we know your misconceptions, we use some common patterns in the back to kind of generate things. And this is from this Dwyer catalog. But then we start to use those as seeds to kind of auto-generate forever, sort of dialing up and down different misconceptions, their likelihoods to generate more and more questions. And each they do look very different. They're truly auto-generated and auto-generated without any LLMs in the back. Like I care a lot about these things being correct. Sujit, I think you had a comment.
Sujit has posted it there that
Oh,
works with some formal language called Z and takes learning curve, but after a point, everyone's like, why don't others get it?
I think that makes a lot of. I mean, I think with a lot of these things, it's pretty steep in the beginning, right? Like it's hard, and when you get it, I think at the very least you fall into a bunch of patterns. But I and what but what I will point out is a lot of experts are like I what's hard about LTL? Um, and what I want to point out here is that like all the people in red and green here are in fact experts. Like one of these was at a triple, like I think the green ones were run at a triple AI special workshop for LTL and LTLF. So these are people who've chosen to come to triple AI, have a special interest in LTL, and they still have accuracy of about 25% on some of these questions. So they're much better than most people. They think they're experts at it, and they are experts at it. Doesn't mean you can't still have these sort of very pernicious misconceptions, that especially around parts of the pattern that you don't yourself deal with in your everyday work, if that makes sense. Like you get really good at specific fragments, but not all of it. So I would love to for this kind of approach with something like Z or even I don't know, even like TLA plus. I don't know, like all of these like much more expressive, even like up to the level of Lean and Isabel. I think it's very possible. I think the idea is once you get the misconceptions, you can plug and play. You just have to provide your semantic mutator. Yeah. Hopefully that. Yes. Okay, great. That's a really good question. Um, so for pick at least, for these three questions, the medians, I put the medians up on screen, but it's sort of 8, 10, 13. It really depends on on the set on the relationships between the sets of of calculations. For example, with regular expressions, in my experience, we converge within 4 or 5 classifications. Um, I suspect part of the reason in this study the classifications were even as high as they were was because humans are not always consistent with their classifications. So Pick has these sort of knobs where you can say, allow me to give one or two, like n like inconsistent classifications before we, force the convergence. So there's like some flexibility we given from the human side, but typically the number of classifications is really low. And I think the point I want to make is it doesn't scale it doesn't scale linearly with the number of candidates. So you can actually have I've had cases where I've had 50 candidates under the hood and still got at my LTL formula in like 5 or 6 classifications because the misconceptions you tend to thrash them out pretty quickly. I think also in the production version of PIC, sorry about this, we have this very sort of a much more sophisticated information sort of strategy to partition candidates so that when you upvote or downvote any one of them, it gives us information about all of them if possible. Uh, yeah, hope that was useful. I guess the word sample is doing a little bit of work here, but there are different languages give you different interesting ways to do the sampling.
Thank you, Siddhartha. With that, perhaps we can conclude the seminar today. Thank you so much for the excellent talk.
Thank you so much.
Yeah. See
Okay.
you. Bye.
See you, everyone.
Thanks a lot.